Okay, so we will go through the practice exam here, but I don't just want to solve those problems in front of you, but I also want to give you a review of the slides that are related to each of these problems. The first problem is related to taking the dual of a linear program, right? So if you you can refer to lecture 7, especially these slides, it kind of gives you a manual of how to take the dual of a linear program, right? It gives you the signs of the variables corresponding to each of the constraints and so forth. Like for here, for all the greater than equal to constraints, the PIs are greater than equal to 0, and for less than equal to PI are less than equal to 0. Then, for a greater than equal to variable, the sign in the dual are less than equal to, and so forth. One of the ways you can solve this problem is you just write down this slide on your cheat sheet, and then you can take the dual, right? It's very easy. But usually I don't want to do that this way. Usually what I do it is to derive the dual using the Lagrangian methods of multiplier, right? You don't really need to put that, that slide down on your cheat sheet. Okay. Yeah. So how do I take the dual of this linear program? So you can associate each of these constraints with a dual variable. For simplicity, let's just assume the signs of the dual variables are the same sign as the constraints. So here, let's just say P1 is less than or equal to 0. And since this is a greater than or equal to constraint, let it to be greater than 0. And then for P3, it's unconstrained, right? Since it's an equality constraint. By the way, if you have solved the homework, please check if I solved it correctly, right? I may did it wrong and you did it correct. You can just tell me I'm wrong. Okay. So now after that, the way to take the Lagrangian dual is that you multiply each constraint by the Lagrangian multiplier and then bring them to the objective. Right? So we have a Lagrangian function which is a function of P1, P2, and P3. In the objective, originally we have 2x1 minus x2. Okay, so now we need to multiply the first constraint, right? Should we just multiply P1 by the left-hand side? Is that correct? Or should it be P1 times the negative of this part? Right? Should be the negative of that part, right? Because whenever you want to bring a constraint to the objective, you want to get a lower bound of the objective, right? So since this left-hand side is less than or equal to 0, you want to multiply the negative of this, and then the negative of this times P1 is less than or equal to 0. Right? That gives you a lower bound. Otherwise, it will not be a valid lower bound. So it should be, if you write it generally, it should be, if a constraint is A transpose X less than or equal to B, and then you put P to be less than or equal to 0, then when you bring it to the objective, you should multiply by P times B minus A transpose X, right? Then since P is less than or equal to 0, B minus AX is greater than or equal to 0, then this whole thing is less than or equal to 0, right? Then you add a less than or equal to component to the objective. Okay, so that's a way you are going to create the Lagrangian dual. If you are not familiar with this logic, you can check lecture 7 again. So that's why we should multiply P1 times the negative of the left-hand side, right, which is minus 2x1 minus 3x2 plus x3 minus x4. And similarly, we have to do the same thing for P2, which would be the negative of that constraint. Right? So the other way you can do it is you can specify P1 to be a greater than or equal to variable. Then you can just multiply the left-hand side, right? It's equivalent. Okay, so since we are dealing with the same sign as this inequality, I will just do it this way. So we can multiply P2 by 3 minus 3x1 minus x2 minus 4x3 plus 2x4. And then you can do plus P3. So P3 is unconstrained, so it doesn't really matter. But let's just, to be consistent, we bring all the variables to the right-hand side. Okay. Yeah. So so we need to minimize over x in the Lagrangian dual, right? So to minimize over all the x, we just collect all the terms associated with x1, x2, x3, and x4. Right? So let's just collect all the coefficients for x1, let's say. So we have 2x1 here. So the coefficients for x1 would be, so here we have a minimization problem, minimize over all the x. So we have 2 minus 2 times P1 times 3P, so it should be minus 3P2, and then plus P3 times x1, right? And then for x2, we have minus 1 minus 3P1 minus P2 plus P3 x2. And then, I will just do the thing real quick. You can check if I did it wrong or not. Then, so this is plus. Okay, so now we have all the coefficients of x1 through x4 ready, but then there are also some constant term related to the piece, right? So the constant term are 3 times P2 plus 6 times P3 here. Okay, so now we already have the dual function. How do we get the dual, right? So let's look at the coefficients of each of the terms, right? So for the first term, we have something related to the dual variable times x1. But in the primal problem, it only has constraints on x2 and x4, right? So x1 is unconstrained. Then if x1 is unconstrained, then this coefficient must be 0, right? Otherwise, you just let x1 goes to plus or minus infinity, you have an unbounded problem. Right. So now with this we can write down the dual problem would be, remember the dual is a maximization problem over the dual variables, and then the constant terms are 3 times P2 plus 6 times P3. And since x1 is unconstrained, we just set this term to 0, right? So subject to okay. Now we look at the second coefficient. It's related to x2. But since x2 is greater than or equal to 0, then we are minimizing here. So in that case, let's say we can only have this term to be greater than or equal to 0, right? So if this term is not greater than or equal to 0, you let x2 goes to infinity, the problem will be unbounded, right? So you want a bounded problem here. Then we have minus 1 minus 3 P1 minus P2 plus P3 to be greater than or equal to 0. And for x3, since it's unconstrained, you just set the coefficient to 0. And then for x4, since it's less than or equal to 0, then we just set this term to be greater than or equal to 0. So that's it, right? That's yes.
For the second inequality,
Yeah.
Isn't it minus b2 instead of minus 2b2?
Oh, okay, yeah. Thank you. Yeah, that's a typo. So if you solve, did I do it correctly, or anyone got a different answer? Okay. Yeah, if I did it wrong, please let me know. Okay. Yeah, I don't want to mislead you guys in the practice exam. Then you did it wrong in the real exam. Okay. Any questions? Yes.
For the second one, should it be less than or equal to 0?
You mean this term?
Yeah.
Yeah. So if you have this term to be less than or equal to 0, then you, since x2 is greater than or equal to 0, right? And if you set x, if this guy is less than 0, x2 goes to plus infinity, then this problem will be unbounded, right? So you don't want this problem, dual problem, to be unbounded, because the dual problem is helping you to provide a lower bound. You want the lower bound to be as large as possible. Okay. Yes.
So wouldn't the fourth inequality then not be a greater than, not be a less than, equal to by?
Oh, yeah. Sorry, that's a typo here. Yeah, that's I was thinking about. Yeah. Okay. Other question? For people who solve this exam, how many people solved this before coming to this class? Okay, great. Yeah, so many of you. If I did it wrong, please call me out. Maybe you are correct. I'm doing it wrong. Okay. Yeah. So anything else? Any other typos you find here? Okay. Yeah. All right. Great. Then yeah. So let's talk about the second problem here. It's related to propositional logic, right? Let's go back to, let me see if I have it here. Here, right? So when you, this is the disjunction part. Yeah, so you can take a very quick review of this guideline, right? When you want to formulate a propositional logic in terms of 0, 1 integer variables, we take this form, right? So this is a way of translating any logic proposition into conjunctive normal form, right? If you have a conjunctive normal form, it's very easy to write it in 0, 1 inequalities. So here's the step, right? First, you will remove the implication using this fact. If A implies B, then this is equivalent to the negation of A or B, right? If you have multiple implications, we can apply it recursively, right? First, remove the inner implication, then remove the outer implications. And then you can move the negation inwards by applying De Morgan's theorems. So the negation of A or B is equal to the negation of A and the negation of B. And the negation of A and B, you just change the and to a or, right? The other thing is that you can distribute or over and, right? So this is like a distribution type of rule, which you should be familiar in the very basic arithmetics, right? If you want to distribute multiply over plus, right? This is the same thing here. Okay. Yeah, so now let's solve this problem here. The first thing it says is if x is true and y is true, then z is true, right? This should be very obvious. You just can write the proposition logic as if x is true. Is this too small? Okay, let me zoom in a little. So if x is true and y is true, then it implies z is true, right? That's just the logic here. Then you can follow the first step of the of this procedure here, right? We have an implication. You can just translate the implication to a negation and or, right? So this is equivalent to the negation of x and y or z, right? And now you have a negation outside the parenthesis. You can follow the second step to bring the negation inside, right? So this is nothing but the negation of x or the negation of y or z. Okay. So with that, let's see. Yeah, we should be done, right? This is already in a conjunctive normal form because there's not even a conjunction, right? There's only disjunction. So it's a negation of x or the negation of y or z. So that will be, you just write, since it's a negation of x, that will be 1 minus x plus 1 minus y plus z has to be greater than or equal to 1, right? Okay, that's the first part. Then for the second part, it says if x is true and or y is false. So here it might be a bit confusing what that doesn't mean by and slash or. That means inclusive or. Okay. So you can also do exclusive or, but you can just treat this as a inclusive or. And y is false, then w is false. So you can write the logic proposition as x or the negation of y imply the negation of w. Right? That's a logic proposition here. Any questions so far? Okay. And then we can follow exactly the same protocol, right? You just change this to a negation and or type of form, right? We remove the implication, and this is or. Okay, now the second step is just we bring the negation inside the parenthesis, then it will be okay. So now we've done the first two steps. First is remove the implication. The second is you want to move the negation inside the parenthesis, right? Okay. So now it is still not a conjunctive normal form yet, right? Because the and operator is inside the parenthesis, the or is outside, right? So what you can do is distribute this or operator into the parenthesis. Right? So now it will be something like the negation of x or negation of w and y. Okay, so this is like a distribute rule sort of thing, right? If you look at this particular slide, it is essentially, this slide here, right? Okay. So with that, now we are at a conjunctive normal form, right? You just let this logic to hold simultaneously, then we are done. So the first one is 1 minus x plus 1 minus w have to be greater than or equal to 0. The second inequality is y plus 1 minus w is greater than or equal to 1. Any questions, or did I do it wrong? Maybe. Okay. Yeah. So now let's look at the third one. It says if z and w. Okay, maybe let's start a new column here with problem C here. If z and w are not true, then either x or y. Maybe let's just change it to or here to avoid confusion, then either x or y are true, right? So that's also contains an implication, right? So if z and w are not true, that will be negation of z and negation of w, right? Then that implies either x or y are true, right? That's the thing we want to formulate here. And similarly, I will do it quickly for this problem then. So you first remove the implication, you bring the negation inside, applying the De Morgan's rule. Y. Okay, so now I think we are done, right? After applying the De Morgan's rule, because now there is no conjunction, there is only disjunction here. Then we can write out this inequality: z plus w plus x plus y greater than or equal to 1. Okay. Any questions here? All right. Okay, so now let's talk about the third problem. So it says formulate the following disjunctive program using the big M reformulation. We'll talk about this in the same lecture as well, right? So here we talk about linear disjunctions, right? So the idea is to have a set that represents a union of two polyhedral set, right? Here, as you can see, the linear disjunction can be represented geometrically in this picture. So it means either x is in this set or x is in this set, right? It is called a union of polyhedral sets. And how do we represent that? We can create a binary variable to represent, let's say, where is a big M? Yeah, here's the big M reformulation. We can create a binary variable to represent which disjunction we are in, right? Or which polyhedral set the variable x is in. And it comes with some big M parameter as well. But the trick here is that how do you pick the big M parameter, right? So as you can see here, when yj is equals to 1, then this whole thing goes to 0, right? Then this inequality constraint have to hold. On the other hand, if yj is 0, then you add a big M parameter on this inequality to let this inequality hold trivially. But how large a big M you should pick, I would argue that you should pick a big M parameter such that you are not violating the constraints of the other disjunction, right? For example, if here we have two polyhedral sets here, right? If you are in this disjunction, of course, you have to let those constraints hold, but you also need to pick a big M parameter such that the relaxation of this constraint, if you have a plus big M here, it should let this particular polyhedral set to incorporate this polyhedral set as well, right? Such that you are not violating the other polyhedral sets. Okay, so let's illustrate this concept using this practice example here, right? Okay, so we want to formulate the whole thing as a big M reformulation. Okay. Now, the only thing we need to remove is this disjunction. All the other constraints just stay there, right? So let's just write down all the other constraints. Okay, so that's all the constraints you just copy to the mixed integer linear programming problem. So now let's introduce one binary variable. Why do we only need one binary variable? Because there are only two disjunctions, right? Let's just use a one binary variable to represent if the first disjunction is true, then y equals to 1. On the other hand, if the second disjunction is true, y equals to 0, right? So yeah, if you go back to this formulation here, we are introducing a binary variable for each disjunct, right? Or if you only have one disjunct, you only need one binary variable, because if you have y1 plus y2 equals to 1, then you might just replace y2 with 1 minus y1. Right? So you essentially only need one binary variable. Okay, so maybe let's write down this binary variable here. So let's use y to represent so let's say y equals to 1 to represent when the first disjunct is true. Okay. Yeah. So now let's write down the inequalities for the first disjunct. Okay. So we have u plus v less than or equal to 2 is true when y equals to so when y equals to 1, this inequality is true. So we can multiply by a big M times 1 minus y. Right? Okay. So now the question is, what will be the value of big M we should be putting here? You have a question? What?
So why can't we write just m into y?
M into?
Like m into y instead of m into 1 minus y, and say y is equal to 0.
I don't quite get it.
Like over here, y is equal to 1 represents
Uh-huh.
k is true, right?
Yeah.
But can we write it as my and say y is equal to 0?
Oh yeah, you can do that as well. But then the definition of y will be switched, right? You are saying like y is 0, the first is true, then y is 1, the second is true. You can do that as well. Okay, there's no big difference. You can just, if you already have the solution, you can just switch your y with my 1 minus y here. Right? Okay. Yeah. So now the question is, what will be the value of big M we should be picking, right? So especially when the first disjunction is true, we still want to give a trivial upper bound of u plus v. Okay. So what would be a trivial upper bound for u plus v here? Any thoughts? 1,000 might be too trivial. Let's pick a tighter one. Okay. Yeah. So any other thoughts? Yeah, 12. Yeah. Why do you say that?
Because u and v are between 0 and 6, so if you sum up.
Yeah, exactly, right? So if you have you already have u and v is between 0 and 6, right? So then no matter which disjunction is true, u plus v is less than or equal to 12, right? But you already have a 2 here, so you can pick m to be something like 10, right? So let's remove it by 10, okay? Now you have the second inequality. U plus 2v greater than or equal to 2, right? And you want this inequality to hold trivially when y is 0, right? So probably you need to minus a big M times 1 minus y, right? So then y is 0, you have a constraint that let it hold trivially. Okay. So what would be a good parameter for m here? 2, right? Since u and v are all greater than or equal to 0, u plus 2v must be greater than 0, right? And you already have a 2 here, so you can write m as 2. Okay. And now it comes a little bit tricky part, right? So we have c equals to 3 here. Okay, so if you have c equals to 3, you can just write something like c is greater than equal to 3, less than equal to 3, right? But then on the right-hand side, you might need to have a big M times 1 minus y, right? Yeah, let's do it step by step. And then on the left-hand side, maybe you want to minus another big M times 1 minus y, right? Just to relax these two inequalities. Okay, so now let's think about for the right-hand side, what will be the big M parameter we need? Or do we actually need this term here on the right-hand side? We don't need this term, right? Because even if this disjunction is true, c equals to 1, right? So no matter which disjunction is true, c is always less than or equal to 3. Does that make sense? So you don't really need this logic constraint on the right-hand side, right? So you can erase those. But on the left-hand side, what would be a good value for the big M here? 2, right? Why is that? Because on the other disjunction, c equals to 1, right? So on the other disjunction, on the other disjunct, then you have c equals to 1. In that case, you can say c is greater than or equal to 1, right? And since you already have a 3 here, the m should be, you can just pick m equals to 2 here. Okay. Does it make sense here? If you have a question, feel free to ask here, because those are some very practical concepts you will encounter in a practical problem. Right? If you formulate a model and you want to choose the appropriate big M parameter, you should choose in a non-trivial way dependent on your problem data. Right? And the solver is very sensitive to the value of a big M. The reason is that a large big M will give you a very weak LP relaxation. And then it will affect the number of nodes you solve in your branch and bound. Okay. Yes?
I picked the 4 for the first constraint.
You pick this one?
Yeah.
Yeah, so you pick 4. What will be your argument here?
So because the second disjunct, you are like less equal to 6.
Oh, okay, yeah, you are right. Yeah, I think you are right. That's a very good point. You can check the this constraint as well. Then I think you can pick 4 here. So maybe let's write it down why we pick 4, because the other disjunct have u plus v less than or equal to 6. Okay. Yeah, that's a very good point. Any other questions? You have a question?
I have the same.
Oh, okay, yeah, very good point.
Would it be wrong to have 10 there?
I wouldn't say so unless you have an argument to make. I think maybe we can even tighten this bound as well, I would say. Yeah, as long as you don't pick 1,000 and you pick a number which is good, that will be fine. Okay, yeah. Yeah. Any other questions here? Okay, yeah. So now let's write down the inequalities for the second disjunct. Okay, so we have u plus v less than or equal to 2, and you want like a big M parameter times y, right? Because when y equals to 1, you want this constraint to hold trivially. But here, since the other disjunct have u plus v less than or equal to 2, we don't really need this part, right? You can just remove this. Yeah, actually, you can just remove this constraint altogether, right? Since we already enforce this constraint here, then u plus v less than or equal to 6 would be redundant, right? But if you pick 10 here, then we still need to write u plus v less than or equal to 6. Right? So this would be, we can just remove this constraint here because it's redundant. Because we have, let's name this constraint to be star. Okay. And then the second one is 2u plus v greater than equal to 6 and minus perhaps a big M times y, right? So now let's say what do we pick? A trivial one would be M equals to 6, right? If y is y is 1, then you have 2u plus v greater than equal to greater than equal to 0. So let's maybe just pick 6. I think it can be even further improved by combining it with this constraint here. Maybe let's just leave it with 6 here. Okay. And finally, we have c equals to 1 for the second disjunct. Then you can say c is less than equal to 1 plus m times y greater than equal to 1, right? Since the other disjunct has c equals to 3, we don't really need to add a big M here. But then on the right-hand side, I think we should add a big M of 2, right? Yeah, so that's a rationale for choosing the appropriate big M values. Okay, yes?
Well, I solved it like differently, so I just assigned the binary variable for each disjunct. Like putting left for y1 and putting.
Yeah, that's also fine, right? If I have y1 plus y2 equals to 1, that's also fine, right? Yeah, because I'm just replacing y2 by 1 minus y. Yes?
Why did you choose 6 for the second one?
Why choose 6 for the second? Oh, because this all those variables are greater than equal to 0, right? When y equals to 1, then they are just greater than equal to 0. Yeah. Other questions? Okay. Yeah. So an extension of this problem is that if you have two disjunctions, what would you do? Or let's say you have a large number of disjunctions. So here we only have one single disjunction, right? So if I put another disjunction constraint, it's like I have a union of polyhedral and then intersect with a union of polyhedral. Okay, so let's write one more constraint here. Okay, but this disjunction is separate from this one, right? And I'm just adding one more constraint. Let's say in one disjunction, in one disjunct, u is greater than equal to 2, and the other one is u to be, let's make up a number less than equal to 1. Okay. In practice, you may have a problem with multiple disjunctions, right? Because one disjunction is deciding between, whether my variable is in this set or that set. And you may add one more constraint related to other variables, right? Saying like whether u is greater than equal to 2 or u is less than equal to 1, right? So there's nothing special here. You just translate this disjunction using the big M as well, right? And add those constraints to your problem. Okay, yeah. I'm not going to do it now. But I'm kind of hinting I will give you a problem with two disjunctions in the exam. So you can try for this problem and then, yeah. Yeah, yes.
Can you repeat what you just
Yeah. So what I said is that this problem only has one disjunction constraint, right?
Yes.
So what if I give you another constraint, which is a disjunction u greater than equal to 2, u less than equal to 1, right? So what you do, you just follow the same procedure to translate this into a big M type of constraints. That's it. Translate the two disjunctions separately into big M. Of course, you are going to create another binary variable for this disjunction, right? That's what I'm saying.
Okay.
Yeah.
And we do that separately?
Yeah, separately, right? Because this is like adding one more constraint on top of this constraint.
Okay, I see.
Okay, yeah. Okay, yeah. Yes.
So then, like if I say y1 and y2 are the binary variables,
Mm-hmm.
so then there's some of the one.
Yeah, yeah. So you define y1 and y2 for these two disjunctions, right? That's what you are saying.
No, like for separate.
Oh, for separate, yeah. Then only this, yeah. So let's use your notation, okay, or maybe use my notation. I have a binary variable y1 to represent when this disjunction is true, right? So y1 is 0 when this disjunction is true. Y1 is 1 when this disjunction is true. But now you have another variable y2 here, which represent when y2 is 1, then this disjunct is true. When y2 is 0, this disjunct is true. But there is no relationship between y1 and y2, right? Those are two separate logic. But in some cases, if you want to enforce logic between y1 and y2, you can do that. But that's another constraint. For example, if you want to say y1 imply y2, you can add on top of that. But we are not having that constraint, right? So that is something called generalized disjunctive programming. You can add some logic propositions on top of the disjunctions, right? Albert, I believe you are working on that in your PhD, right? Okay, yeah, so maybe you can talk to Albert if you are curious about it. Okay, yeah. Okay, any final questions here? Yeah. And then the fourth question is related to KKT conditions and Lagrangian dual, right? So for KKT condition, it should be quite straightforward. Right? Everyone should have some memory of KKT condition. Basically, we have a primal feasibility, dual feasibility, stationarity conditions, and complementary slackness. Right? Those four conditions. You just write them down here. So here, let's say, what would be the primal feasibility constraint? Primal feasibility, you just write down all the primal constraints, right? And x1 plus x2 greater than 0. Okay. And then what about dual feasibility constraints? Okay. Yeah.
The third one of the primal feasibility has to be like x1.
Oh, yeah. So, yeah, so it's x1 and x2 are greater than or equal to 0. Yeah. So for dual feasibility, we can associate a dual variable for each constraint, right? So let's just write this as maybe follow the convention. We are going to use the dual variable using the same sign as the constraint. We just do way1 is less than or equal to 0. Way2 is less than or equal to 0. Let's say there are two greater than or equal to constraint. Let's just say way3, way4 are both greater than or equal to 0. Okay, that's the dual feasibility constraints. So has anyone wondered why do we create a dual variable for x1, x2 greater than or equal to 0, but we did not create a dual variable in linear programs for those x1, x2 greater than or equal to 0? Mm-hmm. Yeah, because for linear program, you can use the argument that x1 is greater than or equal to 0 to force. Yeah, so let's go back to this argument here. Where is it? Yeah. So here in linear programs, we did not create a dual for those constraints, right? But where did we use this condition? We use that condition when we are deriving the dual, right? We are use x2 greater than or equal to 0 when we are deciding the signs of the dual constraints here, okay? Right, so since x2 is greater than or equal to 0, we set this to be greater than or equal to 0 as well. Right? So we are using the condition when we are deriving the dual. But if you have a very general nonlinear programming problem, this argument is not as trivial, right? You will have some nonlinear terms involved with x2, right? So that's why we are dualizing those greater than equal to constraint as well. And the other thing you can verify very quickly is that you can try dualize this constraint as well in a linear program and see what happens. Okay, so let's try it real quick and see what happens. Right? So let's say we associate a dual variable for x2 greater than or equal to 0. Let's call it P4. Okay. Yeah. Then what happens when you, okay, so let's circle it somewhere. So this is your coefficients for x2 when we do not dualize x2 greater than or equal to 0, right? But if you dualize x2 greater than or equal to 0 by multiplying it by P4, what's going to happen is that this constraint will add one more term here, right? So it will become -1 minus 3P1 minus P2 plus P3. Oh yeah, so P4 should be, let's say, greater than or equal to 0. Let's say P4 is greater than or equal to 0 here, right? And then you have something like minus P4 times x2 here, right? Okay, so this constraint will be, these coefficients will be changed by adding the dual variable associated with x2 greater than or equal to 0 as well. And then when you are deriving the Lagrangian dual, you no longer need to force x2 to be greater than or equal to 0, right? Because you have already dualized x2 greater than or equal to 0 by bringing it to the objective. Okay, so now x2 is unconstrained. Okay, so when x2 is unconstrained, then in the dual, you need to set this coefficient to 0 instead of here. It is greater than or equal to 0. Okay.
Can you repeat that one more time?
Yeah. Okay. So there are different ways of you can think about dualizing those constraints, right? So in the original linear programming duality, the way we derived that, we did not dualize those bound constraints, right? We just leave that in the primal problem, and then when you solve the minimization problem, you should still keep those bound constraints, right? Okay. So because you have those bound constraints, then when x1 is unconstrained, you just set it equals to 0, right? But x2 is not unconstrained, then we set this part to be greater than or equal to 0, right? Okay, so now if let's say you just multiply x2 greater than or equal to 0 by some Lagrangian multiplier P4 greater than or equal to 0, you can do that. There's nothing wrong with that, right? And then you gather all the terms involving x2 here, and then the coefficients will change a little bit by adding this term here, right? But now since you dualize x2 greater than or equal to 0, you don't have that constraint anymore when you minimize over x2, right? So x2 will be unconstrained if you dualize x2 greater than or equal to 0, right? So if x2 is unconstrained, when deriving the dual, you just set this coefficient to be equal to 0, right? Okay. Then what is this constraint? This constraint is equivalent to what you derived here, right? Why is that? Because P4 is a dual variable greater than or equal to 0. Right? You just move. So this constraint, this coefficients equal to 0 is equivalent to -1 minus 3P1 minus P2 minus plus P3 equals to P4. And by definition, P4 is greater than or equal to 0. Right? So even if you dualize this constraint, you arrive at something that is equivalent to what you originally have. Okay. The only difference is that whether you dualize the bound constraint or not. Okay. Hopefully, yeah. I'm trying to clarify something. If that makes you more confused, then you can just treat as nothing here. Okay. Yeah. Okay, so you can try it yourself and then try to absorb what I'm saying here. Okay, or if you don't quite get it what I'm saying, then you can just treat, in the, if you have a nonlinear programming problem, you want to create the Lagrangian dual, you dualize those bound constraints as well. That's it, right? To remember that without knowing why. But if you want to know why, that's why. Yeah. So here, here's all the, the bound constraints we have, and then we use V3 and V4 greater than or equal to 0 to bring them to the objective. Okay, so the dual feasibility is just to satisfy those constraints. Okay, then we have a complementary slackness, right? Okay, so it's just that the dual variable multiply by the constraint is 0, right? Then it's like 4 minus x1 minus x2 times v2 is 0. And v3 times x1 is 0. v4 times x2 is 0. Right? So that's complementary slackness. And the fourth one is the stationarity constraint, right? With that, you first need to derive the Lagrangian function x and v, which is x1 squared plus x2 squared minus 8. Okay, and then you bring those constraints to the objective. That will be v1 times x2 minus x1 Okay, so this is the Lagrangian function. Then the stationarity condition is just take the partial derivative of the Lagrangian function with respect to x1, set it to 0, and then take derivative with respect to x2 and set it to 0, right? And the rest of the thing is to take derivatives. So let's try to take derivatives real quick. Yeah, let me know if I made any mistakes here. So it's 2x1 minus 8 plus, minus v1 minus v2 minus v3 equals to 0. And then for the second derivative, we have 2x2 minus 1 plus v1 Okay. Yeah, then that's it. Did I do the derivative correctly? Okay. Yeah, so that's a KKT conditions, right? Then the second question is more tricky, right? So the Lagrangian dual function is we are going to take minimization over x over the Lagrangian function, right? So what is this this function here, right? We are minimizing over this function, which is a quadratic function of x1 and x2. Okay. And we've talked about something more general than minimizing over a quadratic function, right? So if you remember in this lecture of Lagrangian dual, okay, so maybe we move a little bit forward, right? Okay, so the main thing we talk about in this lecture is how to derive the Lagrangian dual for a generic quadratic constraint quadratic program. Right? First of all, we need to check whether this minimization over the quadratic function is unbounded or not. And we gave a couple of conditions where it can be unbounded. Right? First of all, when Q is not positive semi-definite, then it can be unbounded, right? You just pick an eigenvector with a negative eigenvalue. And here we also talk about if B is not in the row space of Q, it can also be unbounded, right? So if it does not satisfy these two conditions, we show that for a generic QCQP problem, we have the Lagrangian dual in this formula here, right? Okay, and then this is a pseudo-inverse of Q. Usually, I will probably give you a much easier problem. You just check the whether this Q matrix is positive, definite or not, right? So what is a Hessian of this quadratic problem? Let's say. Right. So if you treat the Lagrangian function as a function of x1 and x2, what is a Hessian of this function? Go ahead.
2 times identity.
Yeah, 2 times identity, right? So the Hessian. How do I write it? Maybe let's say the Hessian of this Lagrangian function is just 2 and 2 in the diagonal, right? So you take the second order derivative, we are only left with those quadratic terms here. And as you can see, this Hessian matrix is a positive definite, right? So of course it has a bounded solution. And the bounded solution can be obtained at those terms equals to 0, right? And then you can just say when the stationarity condition holds, that's when the Lagrangian function is minimized, right? So here the x1 equals to, you just follow those stationarity conditions. X1 is equals to 8 plus V1 plus V2 plus V3. Okay, and X2 equals to okay, so that's a solution of setting the Lagrangian to 0. You got a closed form solution. Now you can just plug in the x1 and x2 into the Lagrangian function, and that's it, right? So maybe let's write it as x1 star, x2 star. Then the dual function, which is minimization over x, or maybe, we should write it as a function of v. L xv is nothing but you plug it back in. That will be the Lx star 1 v and x2 star and v. Okay. Yeah, in the exam, as long as you can get those solutions, you don't really need to plug it back in. It just we are not testing you middle school math here, right? As long as you know the concept. Okay, so any questions here? Plus, where? I had a typo. Oh, I see. So here is, yeah, okay. Yes?
So if you consider x as a vector of x1 and x2,
Uh-huh.
how would you take the derivative?
Consider x as a vector of x1? Yeah, you can do that, right? Then you write the problem in a matrix form, right? Yeah, just like what we did in the lecture, right? So the Q are in the Q lambda are in matrix form here, right? And then, because now we didn't write the Q in a matrix form, we write it in a scalar form, right? Yeah. Okay, so if you are not fluent with that, take a look at lecture 9, then that should be clear to you. All right. Yeah, so the last part of the question are some very short explanation type of questions. The first thing is, say, show that the conic hull of a finite number of points is a convex set. Right. So what is a conic hull? We talk about that in the second lecture, right? So remember this picture. What does it mean to be a conic hull? What is a convex hull, an affine hull, and a linear hull, right? So if you forgot about that, just try to remember these type of pictures. And by definition, okay, let me write it here. So the conic hull of a finite number of points is a set such that x can be represented by a conic combination of those m points. And then all the lambda i's are greater than or equal to 0, right? From 1 to m. Okay, so this is a definition of the conic hull of m points, right? And as you can see, it is like taking all the conic combination of those m finite points, and we want to show that the conic hull of any finite points is a convex set, right? So how to show a set is a convex set, right? The easiest way is that you can show by definition, right? Take 2 points in this conic hull, and you show that their convex combination is also in the conic hull, right? So let's say we pick 2 arbitrary points. Let's call them maybe y1 and y2 from the conic hull, right? Then by definition, there must exist some lambda, right? Some conic combination of those finite points such that y1 can be represented as I from 1 to n. That's called those coefficients to be lambda 1, lambda 1i, okay? And then y2 can also be expressed as some conic combination of those finite points. Let's call those coefficients to be lambda 2i. Oh yeah, so let's call it, yeah. Oh yeah, I should write this as xi here. Right, so those are definitions. We pick 2 arbitrary points from the conic hull. Then we show that for any lambda, maybe use a different letter, let's say alpha. For any alpha between 0, 1, then the conic combination of y1, convex combination of y1 and y2 are in the conic hull, right? So what is any convex combination of y1 and y2? That will be alpha times lambda I1 plus 1 minus alpha times lambda I2, and this times xi, right? So a convex combination of any two arbitrary points in the conical can be represented in this particular form here, right? Okay, and it's very clear to see all those coefficients are greater than or equal to 0, right? So because alpha is a value between 0, 1, lambda 1 and lambda 2 are greater than 0, right? Therefore, each of these coefficients are greater than or equal to 0, then that says, you can express convex combination of y1 and y2 into the as a Corny combination of this finite number of points, such this set is convex. Right? Okay. Any questions here? Okay. So if no questions, I talk about part B. So it is related to a concept called strongly convex. So you consider the least square loss function, right? So this is like a linear least square problem. Maybe I assume all of you guys have studied linear regression before in your previous lecture. So you are using some data x to predict something called y, right? You have n data points, and then you want to fit those parameter beta such that you can predict y very well using these beta coefficients, right? So you can think about the beta as the coefficients in your linear regression problem, right? And then this matrix X, so we can assume the dimension of X is n times m, where n is the number of data points, and m is a number of coefficients or parameters, or maybe let's call it factors in linear regression, right? So if you only have a one-dimensional linear regression problem, m equals to 2, right? So you have a slope and the intersection, right? Okay, and n is a number of data points. Okay, so you are trying to fit a linear model that given x you can predict y, right? And y, of course, the y is an n-dimensional variable, right? You have n data points. Okay. Yeah. So here we gave a hint. The Hessian of f beta is x transpose x. So it's very clear this is a quadratic function over beta, right? Where the Hessian is x transpose x. So what it is asking is when is this function strongly convex? So maybe you don't remember the definition of strongly convex. At this point, we can go back to the notes here. Okay, so here's a definition of strongly convex. It says a function is strongly convex if there exists a parameter m to be strictly greater than 0, such that even if you deduct a quadratic function of x from f, the remaining of this function is still convex, right? So in other words, f is at least as convex as a quadratic function, or as a strongly convex quadratic function. Okay. Yeah. So in this problem, we have a quadratic function already, right? So when is this quadratic function itself strongly convex? Yeah, positive, definitely, right? Yeah, when this quadratic function is positive, this Hessian metric is positive, definitely it is strongly convex because the smallest eigenvalue is this m over 2 parameter you need, right? The smallest eigenvalue is strictly greater than 0. So for B, you can just answer when x transpose x is a positive definite. That's it, right? here it is enough, but I think if you want to answer a little bit more, this is equivalent to saying that the rank of the X is M, right? So if you have the rank of X is M, X transpose X would also be rank M. And then you can show that unless you have a zero vector, then you always have a strictly greater than zero product with X transpose X. Okay. And for C, let's say, this is also a concept we talked about before, where we say we have two formulations of MILP problem. We give you the first formulation is this linear constraint a1x plus g1y less than or equal to b1, and y is integral. Then we have a second formulation here. Where if you include the integrality constraint, these two formulations are equivalent. But what does it mean that K1 is tighter than K2? Okay. Yeah, so you can say something like that, but more specifically, if you look at the lecture notes, let me try to find out which lecture it is. Yeah, so here. Yeah, so we talk about it here, right? How to compare two MILP relaxations. This is lecture 12, slide 11. So maybe I will write it down later on. Okay. So if you are comparing two MILP relaxation, which one is tighter, right? So you want to argue that the LP relaxation of the tighter relaxation is contained in the LP relaxation of the other relaxation, right? And then how do you really prove that one relaxation is contained in the other relaxation, or one polyhedral set is contained in the other polyhedral set, right? And then the way to prove that is every inequalities in the second polyhedral can be implied by the inequality in the first polyhedral, right? And the way to do that is using things called theorem of alternative, right? You can think about there exists some sort of a Lagrangian multiplier for each of those constraints, and if you aggregate those constraints in the first polyhedral, then you can arrive at a constraint in the second polyhedral, right? So for this, you can just refer to the slide. This is lecture 12, slide 11. Let me make a note here. Okay. Yeah, any questions related to the first three problems here? Okay, and then the last one is to ask you to explain why the second order Cohen program can always be represented by a semi-definite programming problem, right? We also talk about that in one of the lecture notes. Let me find it. Okay, so this is the lecture notes we talk about where any second order Cohen constraint can be represented by a SDP constraint, right? So this is a second order Cohen constraint, the norm of a vector less than or equal to t. And this can be represented using this PSD constraint where you have t as the first element and you have the vector x as those off-diagonal elements. And here you have t times the identity matrix. Why these two constraints are equivalent, you can just apply the so-called Scher's lemma. And then you will find out that according to Scher's lemma, these two constraints are equivalent. That's it. Okay. So this is lecture 8, slide 21. Okay. Yeah. Let me pause here to see if there are any questions. Okay.